Researchers have entangled two quantum memories over a 33-kilometer long fiber optic connection, a record and an important step toward the quantum internet. Quantum networks promise to provide the infrastructure for many disruptive applications such as efficient long-distance quantum communication and distributed quantum computing. Central to these networks is the ability to distribute entanglement between distant nodes using photonic channels, initially developed for quantum teleportation and loophole-free test of Bell's inequality. Recently, entanglement distribution has also been achieved over telecom fibers and analyzed retrospectively. Yet, to fully use entanglement over long-distance quantum network links, it is mandatory to know it is available at the nodes before the entangled state decays. Researchers from LMU Europe have now coupled the two atomic quantum memories over a 33-kilometer long fiber optic connection. This is the longest distance so far that anyone has ever managed entanglement via a telecom fiber. The quantum mechanical entanglement is mediated via photons emitted by the two quantum memories. A decisive step was the researchers shifting up the wavelength of the emitted light particles to a value that is used for conventional telecommunications. The researcher says that by doing this, they were able to significantly reduce the loss of photons and create entangled quantum memories even over long distances of fiber optic cable. Generally speaking, quantum networks consist of nodes of individual quantum memories such as atoms, ions, or defects in crystal lattices. These nodes are able to receive, store, and transmit quantum states. Mediation between the nodes can be accomplished using light particles that are exchanged either over the air or in a targeted manner via fiber optic connection. For their experiment, the researchers use a system comprised of two optically trapped rubidium atoms in two laboratories on the LMU campus. The two locations are connected via a 700-meter long fiber optic cable which runs underneath in the university. By adding extra fibers on the coils, connections of up to 33 kilometers in length can be achieved. A laser pulse excites the atoms, after which they spontaneously fall back into their ground state, each thereby emitting a photon. Due to the conservation of angular momentum, the spin of the atom is entangled with the polarization of its emitted photon. These light particles can then be used to create a quantum mechanical coupling of the two atoms. To do this, the scientists send them through the fiber optic cable to a receiver station where a joint measurement of the photon indicates an entanglement of the quantum memories. However, most quantum memories emit light with wavelengths in the visible or near-infrared range. In fiber optics, these photons make it just a few kilometers before they are lost. Using two quantum frequency converters, the researchers increased the original wavelength from 780 nanometers to a wavelength of 1570 nanometers. This is close to the so-called telecom wavelength of around 1550 nanometers. The telecom band is the frequency range in which the transmission of light in fiber optics has the lowest losses. The team accomplished the conversion with an unprecedented efficiency of 57%. At the same time, they managed to preserve the quality of the information stored in the photons to a high degree, which is a condition of quantum coupling. The researchers think that the system they developed could be used to construct large-scale quantum networks and for the implementation of secure quantum communication protocols. The experiment is an important step on the path to the quantum internet based on existing fiber optic infrastructure.